All right, so we've been talking about these transverse waves, and I said that the particles in a transverse wave goes
Here's what
up
I
and
found.
down, just like this particle little here that you see, the red object is going up and down while the wave kind of travels to the right. And so you can see that the motion of this red object is at 90 degrees to the motion of the wave, which is in that direction. This would be similar to, again, the human wave in a stadium where the person's standing up and then sitting back down and then standing up, and the next person is the same thing, and it looks like a wave. But the person itself or that object itself is only moving up and down. And that's what we defined as a transverse wave, and we saw waves in a string and even the electromagnetic wave, waves on water surface looked like that. Now, if I were to look at a longitudinal wave, the difference again is which direction the particle travels in respect to the wave's propagation. So here, my particle is this red line right here. The particles are moving back and forth. And this is a kind of wave that also travels through medium, a mechanical wave. And a very good example for this would be a sound wave. A sound wave is really basically an air pressure wave. If I were to clap real loud, I create an air pressure wave that travels its way across the room, and it happens to vibrate your eardrums, which is what you perceive as sound. And so you see here that the direction of the object in there that is moving, the material that is vibrating in the same direction, although at opposite in some cases whenever it's going the other direction, but it's going left right while the thing is going to the right. And so it's in the same direction or anti-direction as the movement of the wave, but as contrasted with the transverse wave, where the object is moving up and down while this is moving left and right. Here, everything's moving left and right. Well, this is only moving to the right, but you can see that the wave is moving to the right while the um, the particles are vibrating in the same direction. So that's your difference between the longitudinal and transverse wave. Right here, we have light waves on the water surface, waves on the string, and this example would be sound waves, although you could have this traveling through materials and systems as well. Um, Earthquake waves look similar to these as well, but we won't get into that in here. This is another thing that's important that I'd like you guys to pay attention to are what would be, in this case of this wave, what would be the wavelength or the distance from one peak to another. And so each of these could be considered to be a peak. And then the place where it's all spread out would be considered to be like a trough. So from one peak to the other peak, this would be one wavelength of a longitudinal wave. This part is called a compressed area. This part is called a rarefied area. Or this is sometimes called a compression wave instead of a longitudinal wave because of these compressions that are moving to the right. So these are called compressions, and the middle part that is all distributed, they're called rarefactions. Okay, so that's essentially the difference between the longitudinal wave and a transverse wave. Other than that, they both carry energy but do not transfer any particles. You see the particle comes back and forth in here. This part, if this was sound traveling through air, this part of the air, the molecules of the air would just have vibrated back and forth from here, and the actual wave, this pressure point, would keep moving while parts behind it would be um, letting go and uncompressing. Okay, so that's essentially our difference between longitudinal wave and transverse waves. Just remember, it's got to do with the directions in which the particles vibrate. We'll see you in the next video.